Hello and welcome to this A-level chemistry video about bonding, crystal structures and properties. In this video we'll cover the different types of bonding and structures and the properties that these crystal structures have. Chemical bonds are formed so atoms can achieve a full outer shell of electrons. This makes atoms more stable and therefore less reactive. In the periodic table, the elements of group 0 are called the noble gases. That's this column on the right-hand side here. These elements have a full outer shell of electrons, which makes them chemically inert. In other words, they are unreactive, and so they are chemically stable. The other atoms in the periodic table react and form chemical bonds until they have the same electronic structure as one of the noble gas elements. The physical properties and chemical properties of compounds depend on the way in which compounds are held together by chemical bonds and by intermolecular forces. Physical properties are things that can be observed without changing a substance's identity. So this includes things such as melting point, boiling point, and electrical conductivity. Whereas chemical properties describe how one substance reacts with another. For instance, flammability or reactivity with water. The type of bonding within a substance is the type of attractive force holding the atoms or ions together. And there are three that you need to know about. They are ionic, metallic, and covalent. And then there are four different types of crystal structure. And the crystal structure is the arrangement of particles in three-dimensional space in a regular repeating pattern in a solid. And when the bonding is ionic, the crystal structure is of an ionic lattice. And similarly, with metallic bonding, the structure created is a metallic lattice. There are two types of structure that forms as a result of covalent bonding. Firstly, there is molecular, or maybe sometimes called molecular covalent or simple molecular, but the key term there is molecular. Or alternatively, we have macromolecular, sometimes referred to as giant covalent. If an exam question tells you to answer in terms of structure and bonding, you need to make sure that you do just that. So mention what the type of attractive force is holding the particles together, and then how those particles are arranged in three-dimensional space. Particle theory can be used to help explain changes of state. The particles in a solid are held together in ordered rows and a regular pattern, and the particles are not free to move around, only to vibrate about a fixed position. And this is because there are strong forces between the particles holding them in that fixed position. In order to turn a substance from a solid into a liquid, these forces need to be overcome or at least weakened. And so energy needs to be put in for this to happen. And this energy is only supplied once a substance reaches its melting point. Once a substance has been turned from a solid into a liquid, there are still forces between those particles, but they are weaker than previously, which is why the particle arrangement for a liquid is much more disordered and more random than it is for a solid. Breaking these forces is necessary to convert a liquid into a gas, because once a liquid has turned into a gas, those particles have actually got no forces between them. And that's why the gas particles are arranged entirely randomly and entirely separately, and they're very disorganized. And the energy required to convert a liquid into a gas is supplied once a material reaches its boiling point. The amount of energy needed to change state from solid to liquid and liquid to gas will depend on the strength of the forces between the particles. And the type of substance itself, so that means its structure or its bonding, will affect the type of particle a substance is made up of. And so this could mean we're talking about molecules, or we could be talking about ions in a lattice. And this will affect the type of force between the particles of that substance and the strength of these forces. A useful generalization to keep in mind is that the stronger the forces between particles, the harder they will be to separate, and so the higher the melting and boiling points will be for that substance. There are three different types of strong chemical bonds: ionic, covalent, and metallic. For ionic bonding, the particles are oppositely charged ions, and it occurs in compounds formed when metals are combined with non-metals. For covalent bonding, the particles are atoms which are sharing pairs of electrons, and it occurs in most non-metallic elements and in compounds made of non-metals. In metallic bonding, the particles are atoms which share delocalized electrons, and this type of bonding occurs in metallic elements and in alloys. To understand ionic bonding, we need to first remember what ions are. An ion is an atom or a molecule that has lost or gained electrons and become charged, and ions can be positively or negatively charged. When a metal reacts with a non-metal, electrons in the outer shell of the metal atom are transferred. And metals, which are found on the bottom and the left of the periodic table, generally have a small number of electrons in their outer shell. And so, to form bonds and get a full outer shell of electrons, they lose their outer shell electrons. And since electrons have a negative charge, this means that the metal atoms become positively charged metal ions. Non-metals, which are found on the top and on the right-hand side of the periodic table, they have an outer shell of electrons that is almost full. And so they form bonds to fill their outer shell of electrons by gaining negative electrons. And so they become negatively charged non-metal ions. You can predict what type of ion an element will form based on its position in the periodic table. For instance, the metals, which are shown here in red, they will typically lose their electrons and become positive ions. And non-metals, which are shown here in blue, will gain electrons and become negative ions. Ions aren't simply positively or negatively charged. Some ions can be more positive than others, or more negative than others. And so the sign and the size of the charge can vary. And that will depend on the electronic structure of the atom that the ion is being formed from. For instance, the group 1 elements shown here on the far left-hand side, they have all got one electron in their outer shell, which they lose in order to fill their outer shell. And this means that they will become 1+ ions. The outer shell of group 2 elements also has very few electrons in it. You can see from their electronic structures that they all have 2 electrons in their outer shell. And so to fill their outer shell, they lose those 2 negative electrons from their outermost occupied shell. And this means that the group 2 atoms become 2+ ions. In contrast, when we move over to the non-metals on the right-hand side of the periodic table, for instance, group 7, we can see that this outer occupied electron shell is almost full. For instance, fluorine's outer energy level has the electron arrangement of 2s2, 2p5, and chlorine is 3s2, 3p5. So they've both got 7 electrons in their outer shell. And so to fill that outer shell, they gain 1 negative electron, and this means that they become 1- ions. And last of all, group 6 have got 6 electrons in their outermost occupied electron shell, and so to fill that outer shell, they just need to gain 2 negative electrons, and this means they will become 2- ions. So for metal atoms, when they become ions, they lose their outer shell electrons, and so their outer shell is now empty. And this means that their second to last shell, which was already filled, becomes their full outer shell of electrons. It's more simple for the non-metals. When they become ions, they just gain enough electrons to completely fill their outer shell. And so now all of these atoms, when they become ions, have the electronic structure of the noble gases. Some ions are made up of groups of atoms, and these ions are referred to as compound ions, or sometimes as molecular ions. Let's look at some examples that you need to know about. Firstly, the only positively charged compound ion that you need to know is the ammonium ion, with the formula NH4 1+. And the bonding in the ammonium ion looks like this. You can see the 1 nitrogen atom in the middle and the 4 hydrogen atoms around the outside. And we would typically put square brackets around this ammonium ion and then the 1+ in the top right hand side outside those brackets to show that overall it carries a 1+ charge. And then there are 4 negative compound ions that you should know about. First of all, the sulfate ion, which has the formula SO4 2- overall, and here is the displayed formula for the sulfate ion. And then the carbonate ion, which has the formula CO3 2-, and this is its displayed formula. Then there is the nitrate ion, which has the formula NO3 1-, with this arrangement of atoms in the displayed formula. And finally, there is the hydroxide ion, which has the formula OH 1-, which has this very simple displayed formula for its structure. As we have seen, ions are charged particles, and they are formed when electrons are transferred between atoms. Ionic compounds are made up of oppositely charged ions, and so we will have positive ions that have been formed because they have lost negative electrons, and there will be negative ions, and these have been formed because those atoms gained negative electrons to become negatively charged ions. The ions in an ionic compound are held together by strong electrostatic forces of attraction, which is a very complicated sounding phrase, and it's a very important phrase. So let's unpick it. The word electrostatic means that we are referring to positively and negatively charged particles. In this case, we are talking about the ions that are positively and negatively charged. It's an attractive force, and so that means it is holding those ions together. And I'm showing that here with red lines to show that attractive force. You wouldn't need to draw that in an exam. And they're strong electrostatic forces of attraction, and that means that a lot of energy would be needed to break them. And it is this strong electrostatic force of attraction that is the ionic bond. It is the force that holds the ions together. An ionic compound is actually a giant structure of ions, sometimes referred to as a 3-dimensional ionic lattice. And the word giant is referring to the fact that we don't just have one positive ion and one negative ion, we've actually got a huge number of ions. And the word lattice is referring to the fact that we have got a regular repeating pattern throughout the structure. There are 2 main ways of showing the lattice structure of an ionic compound, and I think the best way to demonstrate them is to gradually build them up. And so if we start with a 2-dimensional slice through an ionic compound, you can see that we've got alternating positive and negative ions in a regular pattern. And the electrostatic forces of attraction between these oppositely charged ions will be acting in all dimensions. And so you can see that this ion here has got 4 oppositely charged ions around it in that same plane in 2 dimensions. And if we gradually introduce another layer and another layer and another layer, you can see that this pattern doesn't just repeat in 2 dimensions, it repeats in 3 dimensions as well. And so every ion will actually have 6 oppositely charged neighbours, and those electrostatic forces of attraction will be between that ion and all 6 of its neighbours. And so they're acting in all directions. And the arrangement of ions that I'm showing here will continue in all directions as well. I'm just showing a small sample of a 3-dimensional lattice. Sodium chloride, which is the only lattice that you need to be able to identify and recognise, would have billions and billions of ions in it. I'm just showing a small snapshot of that lattice structure. Another way to show the lattice structure is to have a cube marked out by lines and to have each of the oppositely charged ions at the points where the lines meet. And so you can see that the 2 different structures do look similar. They have in common the fact that they have both got different particles. What's different in the second one is that the charges aren't shown, but I have included a key showing that the blue ions are the positive sodium ions, Na+, and the yellow circles are representing the chloride ions, Cl-. Both of these diagrams are showing the lattice structure of sodium chloride, but in slightly different ways. And you need to be able to recognise diagrams like these as showing ionic compounds, and the big clues are of course the positive and negative charges, either shown on the ions themselves or in the key. All compounds have a formula, or if we were talking about 2 or more compounds, we would say 2 formulae. Formulae typically show the number of atoms of each element in a compound. For instance, water has the formula H2O, meaning 2 atoms of hydrogen and 1 atom of oxygen in that molecule. Carbon dioxide is CO2, meaning 1 atom of carbon and 2 atoms of oxygen. However, for ionic compounds, for instance sodium chloride, there will be a huge number of ions in a 3D lattice. For example, in 1 grain of table salt, sodium chloride, there are typically 1.2 times 10 to the 18 sodium ions. So clearly we couldn't write the formula for a grain of salt as NaCl with those numbers in subscript, as the numbers would be far too big. Instead, we use something called the empirical formula. The empirical formula shows the ratio ions combine in a 3-dimensional lattice. For example, sodium chloride has the formula NaCl, which means there is 1 sodium ion for every chloride ion. And similarly, magnesium oxide is MgO, meaning 1 magnesium ion for every 1 oxide ion. And there could be billions and billions and billions of each of these ions, but they are present in a ratio of 1:1, meaning there is an equivalent amount of each of them. For calcium chloride, the formula is CaCl2, meaning that for every 1 calcium ion in this compound, there are 2 chloride ions. And sodium oxide is Na2O, meaning for every 1 oxide ion, there will be 2 sodium ions. You will be expected to work out the charge of an ion using the periodic table, and then use the charges of both ions to work out the formula of an ionic compound. And the best way to do this is to look for the common multiple of the positive charge and the negative charge. For instance, in copper chloride, copper has got a 2+ charge and the chloride ion has a 1- charge. And so the common multiple here is 2. And so what we need to do is we need to have multiples of 1 or both of these ions until we get the same amount of positive charge as we've got negative charge, because the idea is those charges need to cancel each other out and the compound should not have any charge overall. And so here the common multiple is 2, and so we already have 2 from the copper 2+ ion, and the chloride is 1, and so we need to have 2 of those chloride ions, so that gives us 2 positives and 2 negatives, and the formula would be CuCl2. Remember, a little 2 or any number in a formula needs to be a small number. As a second example, iron 3 bromide. The common multiple on this occasion, because the iron is a 3 plus charge and the bromide is 1 minus, the common multiple is 3. And so we already have 3 for the iron 3 plus, but the bromide we are currently with 1, so we need 3 of those bromide ions to have 3 negative charges overall. And so we would write the formula FeBr3. When you're writing a formula that contains more than one of a compound ion, you need to use brackets in a similar way to how you use them in maths. For example, for magnesium hydroxide, the ions are Mg2 plus and hydroxide is OH1 minus. The common multiple here is 2. Magnesium is already a 2 plus, hydroxide is only 1 minus, so we need a second hydroxide ion. When we write this, we need to write MgOH2, but if we left it like this would look like only 2 of the hydrogen. But we have got 2 of the hydroxide ion, so we need to put brackets around that hydroxide ion, and that little 2 means 2 of everything inside that bracket. One last example, aluminium nitrate, Al3 plus, NO3 1 minus. We need to have a common multiple here of 3, so we need 3 of those nitrate ions, so it would be AlNO3 3. You can see even more clearly why we need the brackets here, because how I've written it right now looks like there's 33 oxygen, but there's of course not. There are 3 of that nitrate ion. So those brackets have gone round the nitrate ion, and we've got 3 of what is inside those brackets. Melting an ionic compound involves separating the ions away from their neighbouring ions in the three-dimensional giant ionic lattice. Remember that the ions are held together by strong electrostatic forces of attraction. And these forces are present whether a compound is a solid or a liquid. As a solid, these attractions are particularly strong because the particles are especially close. And remember that these electrostatic attractions act in all dimensions. And so that means that each negative ion, for instance, will have 6 positively charged neighbours. And there are billions and billions of oppositely charged ions in this three-dimensional ionic lattice, and so large amounts of energy are needed to break the many strong ionic bonds and separate out those ions. And as a result of this, ionic compounds have high melting points and high boiling points. So they only change from a solid to a liquid at a high temperature, and a liquid to a gas at an even higher temperature. Ions are held together in the ionic lattice by strong electrostatic forces of attraction, and in some ionic compounds the attractive forces will be stronger than in others. In general, the stronger the force of attraction between ions, the stronger the ionic bond, and the higher the melting point or boiling point of a compound. And the strength of this attraction between ions depends on 2 main things: the magnitude of charge of the ions and the size or radius of the ion. These 2 ideas can be combined into one concept called charge density, which literally refers to how densely packed the charge is for an ion, or how concentrated the charge is for an ion. For example, if we consider sodium chloride, magnesium chloride, and aluminium chloride, we would expect that since aluminium is a 3 plus ion, magnesium is a 2 plus ion, and sodium a 1 plus ion, that the aluminium 3 plus would have the highest charge density because it is packing a lot of charge into a small ion. And so the attraction between aluminium 3 plus and chloride is greater than for the chloride and magnesium 2 plus. And so the melting point of aluminium chloride will be greater than magnesium chloride, which is greater than for sodium chloride. As a second example, for the chlorides of the elements in group 1, since all of these positive ions have a 1 plus charge, any difference in melting point must be due to the radius of the positive ion. And since lithium is the smallest ion, it will therefore have the highest charge density because its positive charge is concentrated into a smaller volume ion. And therefore the melting point of lithium chloride will be greater than that of sodium chloride, which will be greater than that of potassium chloride. Electric current is the flow of charged particles. And so to conduct electricity, a substance needs to have charged particles in its structure, and those particles must be free to move. Ionic compounds, which are made up of positive and negatively charged ions, do not conduct electricity as a solid. However, when melted or dissolved in water, the forces between the ions have been weakened and they are no longer held in the rigid, solid, three-dimensional giant ionic lattice. And so therefore now they are free to move around as a liquid ionic substance or as a solution. And so this means that now the charged particles can flow and the ions would move in a particular direction and conduct electricity. And so therefore, ionic compounds do conduct electricity when melted, that means when they are a liquid, or when they are dissolved in water, and we might say that they are in solution. Covalent substances are formed when atoms share pairs of electrons to fill their outer electron shell and become stable. The shared pair of electrons is a covalent bond, and it's the covalent bond, that shared pair of electrons, that holds the atoms together. And the covalent bonds between atoms are very strong, which means that they are very difficult to break. It requires a lot of energy to separate the atoms out from that covalent bond. And the type of atoms that form covalent bonds are nonmetals. They bond together by sharing electrons. And this makes sense if you consider the fact that generally nonmetals need to gain electrons to fill their outer shell that is usually almost full. And so if two atoms both need to gain electrons, the only way that they could do that is by sharing electrons, because they couldn't transfer electrons between one and the other and then both have a full outer shell. Molecules are formed when two or more atoms are joined together by covalent bonds. As well as their name, all molecules can be represented by a molecular formula, and this shows all of the atoms of each type of element that are held together by covalent bonds in the molecule. For instance, hydrogen is H2, chlorine is Cl2, oxygen is O2, and nitrogen is N2. These four elements are all diatomic molecules, and di means two, and atomic is referring to atoms. So they are molecules made up of two atoms. The compounds are more complicated. Water is H2O, and that means it is made up of two atoms of hydrogen bonded to one atom of oxygen. Hydrogen chloride is HCl. Methane is CH4, meaning one atom of carbon and four atoms of hydrogen, and ammonia is NH3, one atom of nitrogen bonded to three atoms of hydrogen. We can also represent covalent substances using a displayed formula. And when we draw displayed formulae, we use lines to represent the shared pair of electrons in the covalent bond. And these lines usually look like large minus signs if they're horizontal, or they can look like L's if they are shown vertically. And what they're doing is they're representing the covalent bond, the shared pair of electrons. And so they are equivalent to one dot and one cross sandwiched together from a dot and cross diagram. And displayed formulae show all of the bonds in a molecule. So they don't just show which atoms of each element a molecule contains, it shows how they are bonded together. So for instance, in this molecule of ethane here, you can see that there are two carbon atoms sharing a covalent bond, and each of those two carbon atoms has got three hydrogen atoms coming out from it at each of the compass points. We normally show displayed formulae as up, down, left, right at 90-degree angles to each other, but each of those sticks is showing a covalent bond. There are two specific molecular crystal structures that you need to know about. The first is iodine, which is a diatomic molecule with the formula I2. Since iodine is in group 7, it has 7 electrons in its valence shell. I'm showing one iodine atom with 7 dots for its valence electrons and the other with 7 crosses. When they bond together, their valence shells overlap and we get a shared pair of electrons, which is the covalent bond. Notice that each iodine atom also has 3 pairs of electrons not involved in bonding, known as lone pairs of electrons. We see the same electron arrangement with the simple dot and cross diagram that doesn't show the actual shells itself. We've got a single covalent bond here, this shared pair of electrons represented by 1 dot and 1 cross, and then each iodine atom has 3 lone pairs of electrons around its outer shell. The displayed formula of iodine shows 2 iodine atoms and a single line representing that single covalent bond. The crystal structure of iodine is as a molecular crystal, where each molecule has a strong covalent bond between the iodine atoms, with regular layers of iodine molecules held in place by weak intermolecular forces that I'm showing here with the red dashed line. There would be more forces than I'm showing here. These dashed lines are just illustrative of the intermolecular forces, which are much weaker than the covalent bonds shown as the purple lines. Water has got the chemical formula H2O, which means it has 2 atoms of hydrogen, each with 1 electron in their outer shell, and 1 atom of oxygen with 6 electrons in its outer shell. When those atoms all come together to make the water molecule, you can see that we've got a covalent bond between 1 atom of hydrogen and the oxygen. That's a shared pair of electrons. And we have another shared pair of electrons between the other atom of hydrogen and the oxygen. And then oxygen has retained 4 of its electrons in 2 separate pairs, and they did not get involved in bonding because hydrogen only needed 1 additional electron. And then the simpler dot and cross diagram also clearly shows the 2 shared pairs of electrons in each of the bonds and the 2 non-bonding pairs of electrons. For the displayed formula for water, that has got 2 hydrogen atoms, each with a line pointing out from it to a central oxygen atom, but the displayed formula only shows the covalent bonds, not the lone pairs of electrons. The crystal structure of water is simple molecular, like iodine is, and there are strong covalent bonds between oxygen and hydrogen. This time, the intermolecular forces hold water molecules in an arrangement that maximizes the stability. In liquid water, there are intermolecular forces between the water molecules, but the molecules are very close together. Whereas in solid water, the most stable arrangement is to have a large separation between the water molecules, as you can see from this large gap here. And this means that solid water is less dense than liquid water, and so ice floats on top of liquid water. Atoms in covalent molecules don't just form single bonds. Double or even triple covalent bonds can form too. Oxygen is in group 6 of the periodic table, meaning it's got 6 electrons in its outer shell. So I'm showing 1 atom of oxygen as having 6 electrons that are crosses, and the other has got 6 dots. Now this outer shell can hold 8 electrons, so the oxygen atoms actually need to share 2 electrons each. And so when those shells overlap, we have in fact got 4 shared electrons in 2 pairs. And so this means that we are creating what is called a double covalent bond. Previously, the single lines, the single pair of electrons is a single covalent bond. Here we have got a double bond. And we can see the same picture for the dot and cross diagram, only without the shells. We're still showing 4 electrons in the middle in 2 pairs. That's the double covalent bond. And we've still got those 4 electrons on each of the oxygen atoms that are not involved in the bonding. which is how those oxygen atoms have achieved a full shell by getting a total of 8 electrons. The displayed formula looks a little bit different here. Instead of having one line between the two oxygen atoms, we have got 2 lines representing that double covalent bond. Dative covalent bonds, also known as coordinate bonds, contain a shared pair of electrons in the same way as a regular covalent bond. The difference is that in a dative covalent bond, both electrons in the pair are supplied by one of the atoms. To distinguish it from a regular covalent bond, a coordinate bond is represented using an arrow instead of a line. So in a covalent bond, we see one electron from each atom, and it is represented using a line. Whereas a dative covalent bond, both electrons come from the same atom and the bond is represented by an arrow that starts, in this case, at the nitrogen and points to the hydrogen, showing that it is the nitrogen atom that is donating both of its electrons to the hydrogen. Covalent bonds and dative covalent bonds are identical once they have been formed, but we use arrows and lines to show how the electrons were originally shared or donated. And so to form a dative covalent bond, we need an atom with a lone pair of electrons, so it can donate that pair of electrons into the dative covalent bond, and we need an electron-deficient atom with room in its valence shell to accept that electron pair. Let's look at a few examples of when dative covalent bonds form. Firstly, in the formation of the ammonium ion from ammonia and a hydrogen ion. Well, the nitrogen atom in ammonia has a lone pair of electrons, which it donates to the hydrogen ion and forms this dative covalent bond shown here by the arrows. For this, we use square brackets around our compound ion, and we use a 1+ charge in the top right-hand side to indicate that the charge is spread over the whole of the compound and it's carrying a 1+ charge overall. Another example is the hydronium ion, H3O+. This time it's an oxygen atom that donates both electrons into the coordinate bond, and it shares these electrons with the hydrogen ion, and we represent this using the arrow again rather than a line. Another example is when hydrogen fluoride bonds with a hydrogen ion. This time a pair of electrons from the fluorine atom is donated into the coordinate bond with the hydrogen ion to form this compound ion here, and again here is the coordinate bond. In one final example, we see NH3 bonding with BH3. And in this case, we have the nitrogen atom in the ammonia with a lone pair of electrons, and the boron atom is electron deficient because it actually only has 6 electrons in its valence shell. And so the nitrogen atom donates both of its electrons into the dative covalent bond, sharing those electrons with the boron atom, as you can see with this arrow in the products. And as you can see in this last example, coordinate bonds don't always have to involve something having charge. Electric current is the flow of charged particles. To conduct electricity, the charged particles must be free to move. So for a material to be a conductor of electricity, it needs to contain charged particles in its structure, and those charged particles must be free to move. Substances that are made from molecules do not have an overall electric charge, as they contain covalent bonds where electron pairs are shared, and so as a result, small molecules do not conduct electricity. When melting and boiling substances made up of small molecules, the particles being separated during the change of state are the molecules. And a molecule is 2 or more atoms chemically joined together by sharing pairs of electrons to form a covalent bond. I'm showing 5 examples of molecules that could make up a particular substance. These types of substance only have weak forces between their molecules, known as intermolecular forces, where inter means between, and so between molecule forces is the literal meaning of their name. And since these forces are weak, they need very little energy to overcome, and so small molecules have relatively low melting and boiling points, which means that substances that consist of small molecules are usually gases or liquids at room temperature, which is taken to be 20 degrees Celsius. And these substances are liquids or gases at room temperature because the molecules that make up the substance have enough energy to overcome the intermolecular forces, those forces between the molecules holding the particles close together. I go into more detail about the different types of intermolecular forces and electronegativity that is one of the causes of these forces in a separate video. For now, for this video, I'm going to generalize and refer to them all as intermolecular forces. Boiling water is a really useful example that illustrates the connection between intermolecular forces and melting and boiling substances made of small molecules. When you fill a kettle, it is of course full of water in the liquid state. And you can see this from the particle arrangement that I'm showing inside the kettle. On the right-hand side, I'm showing an enlarged diagram of the interaction between 2 water molecules. And you can see that inside each of the water molecules, there are 2 covalent bonds, and I'm showing those covalent bonds as grey sticks. And then there is the intermolecular force holding the molecules close together, and I'm showing this as a dashed line connecting the 2 molecules. And so the dashed line is the intermolecular force, and the grey sticks are the covalent bond. As the water boils, energy from the kettle is transferred to the water molecules, and these particles use the energy to overcome the intermolecular forces holding it in the liquid state, and so it starts to turn into a gas, and some of the molecules will leave the kettle. As time passes, more and more particles will turn from a liquid state into a gas, and then the kettle will switch itself off and keep most of the boiled water inside the kettle. We might call what comes out of a kettle steam, but it is still water. It's just now in the gas state, and you can see that from the particle arrangement of the water molecules that I'm showing that have escaped the kettle. They are very randomly arranged, and there is a large gap between the molecules. But importantly, they are still recognizable as the same water molecules that were present inside the kettle. Since the intermolecular forces are weak compared with covalent bonds, it is the intermolecular forces between molecules that are overcome when a substance melts or boils, not covalent bonds. All of the covalent bonds in a molecule are still intact once a substance made of molecules has boiled. These are called giant structures because they're made up of a huge number of atoms, and they are giant covalent structures because those atoms are held together by a large number of strong covalent bonds. Examples of giant covalent structures include silicon dioxide, sometimes referred to as silica, which is the main component of sand and many rocks. Also, we have got graphite and diamond. Both of these last 2 are giant covalent structures made from carbon. The atoms in a giant covalent structure are arranged in a giant lattice. And giant, again, is referring to the huge number of atoms, and the lattice is referring to a regular repeating pattern within the covalent structure. In this giant lattice, each atom is bonded to several others in an extensive network. When we get to the edges of our diagram, it isn't always obvious that this does continue, but you need to know that when you see a diagram like this, you are just seeing a small snapshot of a larger structure. As a result of this giant covalent lattice, the structures themselves are very strong and very stable. To understand the properties of diamond, we first need to know about its structure and bonding. Diamond is made of the element carbon, and only carbon. And since there aren't any other elements involved, the formula for diamond is actually just a capital C. In a diagram of diamond, the carbon atoms are usually represented as black circles, and there are sticks coming out of these circles, and these sticks are representing covalent bonds connecting the carbon atoms together. And covalent bonds, remember, are shared pairs of electrons that hold the carbon atoms in place. The structure of diamond contains a huge number of carbon atoms in a giant covalent structure, sometimes referred to as a lattice, which is a generic phrase which just means a regular repeating pattern. On this occasion, that repeating pattern is a tetrahedral shape around each atom of carbon. I'm just showing a small section of a larger lattice here, but this would of course continue in 3 dimensions and probably cover billions and billions of atoms of carbon. As you can see from the diagram, each carbon atom is forming 4 covalent bonds with other carbon atoms. And to do this, it uses all 4 of the electrons in its outer shell, combining with 1 electron each from each of the 4 carbon atoms that each atom is bonded to, and this gives every carbon atom 8 electrons in total. You might think that the carbon atoms at the edge of my picture don't have 4 bonds, and that's just simply because we have to end the diagram somewhere. These atoms do have 4 bonds. The diagram would just look a bit messy if we were to show all of them. There are 3 properties of diamond that you need to know about, and each of them is caused by the structure and bonding of diamond. First of all, diamond is a very hard substance, meaning it resists being deformed and its surface can withstand penetration, abrasion and scratching. And the reason that diamond has this property is due to its giant structure, where each carbon atom forms 4 strong covalent bonds to other carbon atoms. And these bonds are difficult to break, and this requires a lot of energy to break them. And so as a result, no carbon atoms can move in this rigid 3-dimensional tetrahedral structure. The second property is that diamond does not conduct electricity. And this is because it has 4 covalent bonds per carbon atom in the structure. And each covalent bond is made up of a shared pair of electrons, and so each carbon atom uses up all of its outer shell electrons, those valent electrons. They are all used in bonding. And so as a result of this, there are no delocalized electrons to move through the structure and carry charge, and so diamond does not conduct electricity. And the third and final property of diamond is that it has a very high melting point. Unlike for simple molecules, where you need to overcome the forces between molecules, giant structures contain a large number of covalent bonds, and you need to break this huge number of covalent bonds in order to separate out the atoms. And covalent bonds are very, very strong, and so a lot of energy is required to break them, and you only have enough energy to break them at high temperatures, hence the high melting point. Graphite is a giant covalent structure, meaning it's made up of a huge number of carbon atoms in a repeating pattern. Each carbon atom, shown as a black circle in my diagram, forms 3 covalent bonds, which are the black lines, to 3 other carbon atoms in this structure, resulting in layers of hexagonal rings. Remember, carbon has 4 electrons in its outer shell, and it only uses 3 of them to form each of the covalent bonds. And so as a result of that, 1 electron per carbon atom is delocalized, meaning this electron isn't in a fixed position and can move through the structure, similar to in metals. In this structure, you can see that there aren't any covalent bonds between the layers. There are no black lines anywhere between these layers of hexagons. But what there are is weak intermolecular forces, and these forces hold the layers together. And sometimes they aren't shown on diagrams, but I'm doing so here, showing those intermolecular forces as purple dashed lines. Do remember that these layers continue off in both directions, and so the intermolecular forces do as well. And there are also going to be more than 3 layers, but I'm just showing a portion of graphite structure here. The structure and bonding of graphite gives rise to 3 important properties that gives graphite some of its uses. First of all, graphite is soft and slippery, which enables it to act as a lubricant and reduce friction. The reason that graphite has this property is down to its layered structure of interlocking hexagonal rings. There are only weak intermolecular forces between these layers, so this means weak forces of attraction and no covalent bonding. And therefore, the layers can slide over each other and separate. This also makes graphite really useful in pencils for making a mark on paper. When you use it in this way, you are literally rubbing or breaking off a layer of the graphite onto the paper. Graphite also has the property of being able to conduct electricity, which allows it to be used in electrolysis as the inert electrodes. In the structure of graphite, there are only 3 covalent bonds per carbon atom, and carbon has 4 electrons in its outer shell. And so 1 electron per carbon atom is delocalized, which means it isn't held in a particular position, and so it can move through the structure carrying electrical charge, because electrons themselves are negatively charged, remember. The final property of graphite is that it has a very high melting point, similar to diamond and other giant covalent structures, for the similar reasons. And the reasons are that there are a very large number of covalent bonds between carbon atoms that need to be broken in order to separate out the atoms. And covalent bonds are very strong, and so they require a lot of energy to break them, and you only have enough energy to break those bonds at a high temperature, hence the high melting point. When we're talking about metallic substances, we could be referring to metallic elements or to alloys. The majority of elements are metals, and you can see this from the periodic table that I'm showing here, where the metals have been highlighted in red. And metals are found to the left of the periodic table and towards the bottom. Substances made of metals consist of giant structures of atoms, and they're referred to as giant as they're made up of a huge number of atoms. And they are arranged in a regular pattern, and you can see that from this 2-dimensional diagram that I'm showing here. There are clear layers, or you might call them rows. There is a lot of symmetry here. The atoms are all shown as being the same size with good consistent circles, and the atoms are densely packed together. In other words, they are very close together. And these aspects of the structure influence the properties of metals, allowing them to be bent and shaped easily. Normally, you draw a diagram of a metallic structure in 2 dimensions because it's easier and more clear, but it is worth noting that they are 3-dimensional shapes really, and their layered structure and their dense packing of atoms does continue into 3 dimensions really. The electrons in the outer shell of metal atoms are delocalized, and this means that they are no longer in their shell, which is a relatively limited space for them to occupy, and this means that these electrons are free to move through the whole structure. And it's really important to describe their movement as moving through the whole structure rather than any alternative word for through. And you can see this from the 2 diagrams that I'm showing here. On the left-hand side, I'm showing 8 atoms of a metal, and their outer electrons are shown, as is their outer electron shell, as a solid circle. On the right-hand side, that outer shell has been removed because all of those outer shells are merging together and the electrons that were in them have now been delocalized, which means that they are free to move. And the metal atoms have lost a negative electron, and so technically now they are positively charged ions. These delocalized electrons are free to move through the structure, and so technically they could be anywhere in the metal. And so sometimes we actually don't show those electrons at all. The sharing of delocalized electrons gives rise to strong metallic bonds that holds the structure in place. And this metallic bonding is down to the electrostatic attraction between the positively charged metal ions and the negatively charged delocalized electrons. Because the positive ions would obviously repel each other, but they're held in place due to the strong attractions that they have for the many delocalized electrons that are moving through the structure, far more than one attraction at any one time. The one example of a metallic structure that you need to know about specifically and be able to draw is magnesium. The structure of magnesium is a giant metallic lattice of magnesium 2+ ions, arranged in layers with delocalized electrons in a sea around those ions. And the type of bonding present is metallic bonding, which is the electrostatic attraction between the positive magnesium ions and the negative delocalized electrons. And these attractions are very strong and so require lots of energy to break, which gives metals high melting and boiling points. Metallic substances are made up of giant structures of a huge number of atoms with strong metallic bonding, and this is due to the strong electrostatic forces of attraction between the positively charged metal ions and the negatively charged delocalized electrons. And you can see that on this diagram here. The metal atoms have lost electrons, so they're being shown as positively charged ions, and there are delocalized electrons spread through this structure, and I'm showing with the blue dashed lines the electrostatic forces of attraction that are present between the ion and the delocalized electrons. You can see that there are lots of attractions being shown here, which is what contributes to the strong metallic bonding in the structure. As a result of this, metals have high melting points and high boiling points, since a large amount of energy is needed to overcome the electrostatic attractions which constitute these strong metallic bonds, and makes the particles in a metallic substance very difficult to separate. Metallic bonding is the electrostatic attraction between positive metal ions and negative delocalized electrons. The melting point of metals can vary. In general, if the electrostatic attraction is stronger, the metallic bonding is stronger, and so the melting and boiling point will be higher. And this will be the case when the metal is highly charged. For instance, the melting point will be higher if the metal is a 3+ ion than if it was a 2+ ion, and the 2+ ion will have a higher melting point than a 1+ ion. The melting point will also be higher if the metal ion is smaller. And so this smallest 1+ ion on the left-hand side will have the highest melting point of these three, and the middle ion will have a higher melting point than the one on the right-hand side, because the one on the right-hand side is the largest ion. We can combine these two ideas into one by saying that the melting point will be higher if the metal ion has a higher charge density, and this is referring to the amount of charge in an ion per unit volume. Metals are good conductors of electricity because the delocalized electrons can carry electrical charge through the metal. Don't forget that all-important word, through. If we take a look at a zoomed-in cross-section of a metal, we can see the metal atoms that have lost electrons to form positive ions, as well as the delocalized electrons in the metal structure, which are free to move. When we turn on an external direct current, the electrons will all move through the structure in one direction, and this is because they are negatively charged, and so they will all be attracted and move towards the positive terminal. Remember, I'm only showing a small cross-section of a metal here. In one copper wire, there would be billions and billions of delocalized electrons.